Excellent.
Yep.
Let's go on. Thanks.
More about the data for the box rotation.
I have. I think it's. I don't know if you need it or not, but if you use it, it should be related to theta dot, right? It should be equal to.
You mean the data for the cylinder?
Yeah.
Yeah, so the way I did it
It
was
should be like proportional to the different distance between the center or something.
I just ended up with the ratio. The theta for the box rotation is 4b, which is like the box 4b over pi r, which is the center times theta c, which is like a rough approximation.
Okay.
But then I was like, man, there's a lot more numbers in there. So I'm just solving it two different ways. I just have assuming small angle theta b is theta c, and then
Yep.
doing it the normal way.
Okay, and see what
I'm
it
gonna
comes
see,
out.
what it comes out to.
Sounds good. All right, I like it. Okay. All right, well, thanks everybody for coming. I appreciate you guys coming to these Tuesday afternoon sessions. So hopefully this is going to be of use to you. This is the review session, so I kind of haven't planned on talking about anything except maybe going through the book chapter by chapter and seeing what you guys have questions on. So that's roughly the plan. Are there any questions about the structure of the exam first, or what I'm looking for, or what should be covered? It's chapters 1 to 7 that you're responsible for, right? Anything in there is fair game, except maybe if there's some like optional sub-chapters that I didn't cover. But for the most part, there aren't a lot of those. Everybody's okay with chapters 1 to 7? Yeah. Fine.
I guess general, how many questions? Definitely not multiple choice everything.
No. I think this would be 2 to 5 questions, and I typically break them up into subparts to try to lead you through the problem. And so that's how I envision it going. So there, 2 to 5, but the sub-problems don't really constitute different questions in the sense that they're different parts of leading you through how to do a problem. And the advantage of doing that is it helps me grade in terms of, okay, well, I got these 2 parts, they didn't get this part, so that's 2/3 credit or whatever. That makes it real easy for me, and it really makes it, and I hate doing a big series problem where, if you get the wrong answer in the first part, then it propagates and all the other 4 parts are also wrong, because that's not fair to anybody. So this way I have checkpoints where like, okay, well, you got that wrong, but you did the next step right, I can give you credit for the next step. If your previous step, assuming your previous step were correct, and I could do stuff like that. So that's why I like to break it into subparts. So that's kind of what I have planned for the exam. By the way, I'm not going to be here. Did I mention this? I'm going to be out of town. But Gwen is my wife is gonna proctor the exam, so she'll be here. I'll be on text contact if you guys have any issues. I'll be at a leadership meeting for the American Astronomical Society in Washington, D.C. I'm the chair of the Division for Planetary Science, or I will be starting in November, and so I get to do these jaunts to D.C. Periodically. So I'm getting called to headquarters to make sure everybody's on the same page. It's not gonna be that much fun, but there you go. So no class. Sorry, there will be class Friday. I will not be there, but there will be class Friday. That's the exam, and Gwen's just
Don't
gonna
show up, you're just gonna get a 0 on midterm.
It will not go well. It will not go well for you, but it will go fine for me. I will try to get these graded as soon as possible, because we're supposed to get your midterm grades in on Monday. So the goal is to turn these right around and give you guys results on Monday. Next Tuesday at this time is when we're really going to go over the exam. We'll go over the problems on the exam. We'll talk about them. We'll talk about grading and stuff like that. And so I'm not going to do that in class on Monday. I'm going to do that on Tuesday, just because I think it's one of those things that is more easily skippable. And I'm trying to put the more easily skippable stuff on the Tuesday afternoon, since people are going to miss that.
So we can expect problems on the exam that are similar to what we've been doing the homework.
Yes, but easier. I'm not going to ask the hardest stuff that you see on the homework. So Phil, I think you're safe figuring out the rotation of the box. I'm not gonna ask you to do that in 45 minutes, when there are like gonna be like two or four other problems, you know. So keep with that in mind. Keep in mind that, yeah, so it's gonna be the same style, I'm gonna expect the same kind of things, but in general, I'm gonna try to pick problems that will be illustrative, that you understand the process of how to do things. And I'm gonna try to not bog you down in too much algebra, but you know, it's analytical mechanics, there's gonna be some, but I'm gonna try not to make it, you know, we'll probably lose the double pendulum and the rotating box. So that I would expect problems at the level of sort of the 1-star problems in here, maybe some a little more than that, but of that level, yeah.
Calculator?
Yes.
The necessities?
Yes, you're welcome to bring a calculator. You probably won't need it, but I don't want to say that, so go ahead and bring a calculator. It's open book, open note, so you can bring all the other stuff you want. Bring War and Peace, bring, you know, the dictionary, it's all good. But you can't look things up on your phone, obviously, so no internet. Yes.
So are there going to be any questions that would result in an integral complicated enough we would need to
Use your integral
the
table? Maybe. I mean, I'm not going to be looking for really nasty ones, but yeah, there could be cases where having an integral table handy would make it much easier for you than if you had to try to figure out, or just leave it like that and get partial credit. I mean, I'm going to be trying to be pretty liberal with partial credit because I really care more about how you get there. I care about the journey, not the destination. So I want to make sure that you guys are getting to the right answer and you're using the right process more than have you,
remembering
you know,
every single technique of integration ever.
Yeah, right. Rather than did that integrate, did you get the sign wrong on your integrate by parts or something like that. But you can save that step, right? If you have the integral table and just look it up, you know, definitely bring your book. Remember in chapter 1 we talked about different coordinate systems, and remember the back of the book, right, has all these nasty, how to do nasty things like curls or Lagrangians in you know, unusual coordinate systems, spherical polars, cylindrical polars. And those.
The E&M book. The
You're
E&M book has the same.
Yes, you can bring your E&M back. I'm totally fine with that. Because I really want to, I mean, I don't want you need to be able to know that everything's not quite the same if you do it in a different coordinate system, and just look it up. I mean, obviously, this is the kind of stuff that I don't want you to memorize. I'd rather you just look it up and instead learned and practiced doing problems rather than memorizing numbers or formulas, because that's not really what I care about. All right, so going through the chapters, let's go through chapter by chapter. I find this tends to jog people's memories better than just asking for questions straight up. So the first chapter we spent like half an hour on, and we're basically just talking about how things are different in different coordinate systems. What's the same? So you guys should be able to use certainly polar and spherical polar coordinate systems, r theta phi, or r theta, and be familiar with those and comfortable using those additional coordinate systems as necessary. Everyone okay with that? Any questions? That was chapter 1, so it gets harder from there. All right, what was chapter 2 about? I don't remember. Anyone remember? What's chapter 2? Oh, yeah, okay. Projectiles and charged particles. That's when we talked about drag. Different types of air resistance. Okay. And we discussed how there's linear drag, which occurs sort of due to laminar flow, and then there's quadratic drag that occurs due to turbulent flow. I'm really into the qualitative nature of why those are quadratic and linear, as I've asked you questions on that in the homework and stuff. So I mean, it's important to me, more important almost, that you understand why quadratic drag goes as v squared, almost than being able to do problems with it, though it would be nice if you knew how to do problems as well. But remember, you can't really solve quadratic drag uniquely in 2 dimensions in closed analytical form. So that's not something I'm gonna expect you to do on an exam, but I could expect you to do calculations of, you know, what forces would be, what terminal velocities might be, how to get them, how they might change as you change various parameters, stuff like that. All right, the drag wasn't too bad. But any questions about drag? Okay. Chapter 3 started talking about momentum and angular momentum. And the conservation thereof. In linear momentum conservation is pretty straightforward, although it can trip you up when we get to things like collisions that conserve momentum, or the rocket equation where you're conserving momentum, right, with a changing mass. I like the rocket equation because I like rockets, you know. We talked about angular momentum and its conservation. Looks like there's stuff about Kepler's laws. Remember, as we sort of just re-derived actually yesterday on the board, you know, in an orbit, because all the forces are radial, there are no, there's no work done in the tangential direction. There's no torque, no net torque. And so the angular momentum is conserved, and if you guys were ever taught Kepler's second law that, you know, planets sweep out equal areas in equal times, it happens to be mathematically equivalent to the conservation of angular momentum. So it's the same thing. I like angular momentum. Everything in space rotates, so I like it. I use it. You should know about it. Any questions?
So you would say the angular momentum of one would equal the angular momentum of the other one using conservation? Solve for
Pretty simple. No, I mean, you can figure out, you know, you could, let's see, how would you use this? For instance, like the, you know, angular momentum of the Earth-Moon system is sort of conserved if you neglect solar torques. And so there have been torques between the Earth and Moon, and the Earth-Moon configuration has changed, and those tidal forces dissipate energy, but they conserve angular momentum. You can figure out basically how fast Earth must have been rotating as the Moon moved in if you just conserve angular momentum. It's pretty straightforward. So yeah, it might be as simple as, yeah, L before equals L after, but still, it can be important. Okay. Chapter 4, we got to talk about energy. Started talking about path, what I call path integrals. The book calls them line integrals, I guess. What do you guys all call them?
They're the same thing. So.
Well, I know, but you know, I always call them path integrals, but I guess that's what I was taught. Did they teach, what do they call them in math, in the math courses?
Line integrals.
Line integrals?
I know in mathematical physics they're called path integrals.
They call them,
Yeah.
so maybe physics calls them path integrals, and
I think he says line
and then in E&M?
Yeah.
Okay, so there's a,
Like the book says one thing, everybody says.
but as long as you know they're the same,
Line
path
integral.
integral, line integral, be able to do basically integral of force dot ds to be able to get yourself a change in energy. That's important. Forces, of course, the negative gradient of the potential. That's important, and that's something that you definitely use later on, and that you use ultimately once we get further on into Lagrangians. So that's important. Most of this is just prelude, even the energy stuff. Because the stuff I really care about starts at chapter 5. Chapter 5, 6, and 7 is the stuff I really care about. Of course, the first 4 chapters play into what you do in chapters 5, 6, and 7, so that's important. But this later stuff is really the newer stuff, and this is the stuff that I really want to see. That I remember the best when I think about the first half of the course, and so you should too. As far as oscillators, we presumably went into more depth in oscillators than you guys saw in 211. Yes?
Yeah.
Okay, good. So it was, at least there was some new material there. But I know you saw some of that, but maybe didn't see why. You will be expected to solve 2 different types of differential equation. Okay? Basically, And, okay, what's the solution to this one?
E to the x.
Yeah, what,
the
root cx in this case, okay? What's the solution to this one? Sine or cosine. Those are the ones you should know and love and be able to just look at this and be able to solve. Because you know the answer. There aren't that many type of differential equations. I'm not gonna throw you a new differential equation that you have not seen before on the exam. I will go, however, reserve the right to throw differential equations you have seen before. So, those are kosher. Looking at harmonic oscillators. Oh yeah, we went through like Lissajous figures and stuff. Those were fun.
You want us to graph those for us?
I mean, I could ask you to do that. That's probably not something I would ask you to do. I'm just thinking, you know, because there's kind of no process. Remember, I'm more interested in you understand the processes, and that's all. Plug this number in, and what does the picture look like? So that sounds like more of a, you know, more of something I'm not gonna be interested in asking you on an exam, I would guess, but, you know. Let's see, damped oscillators, we talked about different damping levels in oscillators, and you should definitely understand the difference between underdamped, overdamped, and critically damped situations. What drives either of them, what drives each of them, how the solution to the differential equation changes in each case, what the differences look like, how, and really I'm looking at, I really care about sort of like, can you recognize what that solution is gonna look like as a function of time, and what the different various things represent. Remember we had, what, omega naught, which is the undamped natural frequency, and then we had omega 1, which is the damped, the frequency is affected by damping, and then we have omega, which we'll get to in a second, the forcing frequency. Definitely know what you're talking about. Make sure you can keep your omegas straight, because they can get a little hairy. Make sure you understand sort of the concept of damping and the various damping parameters. Remember we talked about the beta parameter, which is, you know, ultimately a hodgepodge of different things. But we also talked about Q, the quality factor. Everyone remember what that is? What's the quality factor again?
Something like how long it'll take. The function seems like how long it'll take to decay some really high quality factors like quartz crystal or something.
Right,
like
something
that.
has low dissipation. So, right, yeah, Q is equal to omega naught over 2 beta. But it's a different way of thinking about dissipation in terms of the number of oscillations you go through before the amplitude decays, rather than beta, which is a sort of a time period over which that decay happens. We also talked about, approximating forced damped oscillators as Fourier series. I'm not gonna be able to ask you to like do complex Fourier integrals on the exam, okay? But you should be able to intuitively understand that the way you can solve a non-sinusoidal forcing pulse is by approximating as a series of sinusoids, and then understanding that the ultimate solution then is going to be a superposition. The ultimate motion, resulting motion of the oscillator is going to be a superposition of the various resulting oscillations that would result just from those different individual Fourier terms. We spent one day on that. I'm not going to ask you to do like a whole calculation probably, but I want you to be familiar with it. Questions about oscillators? All right, so we're getting to the hard stuff then. Okay, chapter 6 was all about math. It's all about the Euler-Lagrange equation. What's the Euler-Lagrange equation? You should know this one off the top of your head.
Delta L, partial of L with respect to x is, or partial of F, I guess they use, is with respect to x is equal
So all of chapter 6 is basically prep for chapter 7, right? It's all about deriving this and being able to use this, and then the ultimate function we're trying to minimize is the Lagrangian. Remember that this gives you a stationary point, not necessarily a minimum. I mean, you want it to be a minimum, you hope it's a minimum. It might not be a minimum, it could be a maximum, it could be an inflection point, right? It could be a saddle point on the way by. You don't a priori know which one of those it's going to be, so do be a little bit careful, make sure you're finding a true minimum in terms of the path. What kind of questions can I ask you about just, you know, path minimization, Euler Lagrange stuff, calculus of variations, that you can solve in 15 minutes?
What's the shortest distance between 2 points?
Yes, and in fact, I'm going to reveal right now that I thought about it and I was like trying to find a question to ask, and that's the only fucking question the only question I could ask from this chapter that makes any sense, and I just thought it was lame. So I'm not going to ask you a specific question separately about this, because naturally all of the chapter 7 uses that. So I decided the one I'm going to use is not, I'm not going to have you calculate the shortest distance between 2 points for what, like the 6th time, okay? Because that's like kind of stupid. And instead, I'm going to ask you to do all your chapter 6 calculus of variation stuff is going to come in terms of chapter 7, which is the physics. So I like that better. You like that better. The shortest distance between 2 points is still a straight line. I think we have that completely nailed. I don't think there's any reason to, you know, beat that dead horse. That's fine. So I will not ask you to do that on the exam. Chapter 7 then. This is the one I care about. So we're trying to essentially redo all of Newtonian mechanics, all of what you've learned up to this point, in terms of a totally different mathematical approach, which is by minimizing the Lagrangian. The Lagrangian is, of course, remember,
T minus U.
T minus U. Remember the minus sign. Kinetic energy minus the potential energy. Okay? What are the steps you should follow to solve a Lagrangian problem? Okay. So first, write the Lagrangian in the inertial space. And use it. Don't get fancy here. Write it out 1/2 mv squared, you know, just be real straight up. Don't try to get too excited. But make sure that you account for all of the kinetic energy in a problem. Okay, if the pulleys can move, make sure you include them. Make sure you include them as rotational kinetic energy, which is
1/2 I omega squared.
1/2 I omega squared. Okay, what's step 2?
Generalized coordinate system.
Find your generalized coordinates Qn. Pick something rational where the thing is usually following, you know, you can reduce a 2-dimensional problem into 1 dimensions by following along a path, or by, you know, having your dimension be an angle around a central point. Do that. Do something that makes your life easier ultimately, because unlike with polar spherical coordinates or something, right, where you had to, then you know all the math is different. The whole point of the Lagrangian is that you don't have to worry about different math and crazy invented coordinate systems. So use that to your advantage. Pick something that's going to help you. Okay, step 3.
Rewrite the Lagrangian.
Okay. Rewrite the Lagrangian in terms of the various Qn. And then step 4,
Euler Lagrange.
apply Euler Lagrange. Okay. That's it. Should we do some practice problems? I'd like to, but I have to find practice problems to do, so.
More,
No.
Triple pendulum? What? Yeah.
more generally, can you go back over
Yeah.
damping?
Yes, okay. So back to chapter 5. So we determined that for an oscillator with no damping, we decided that, what was the position as a function of time? So this is undamped, just a pure oscillator, you let it go, it goes wing.
A sine of omega t plus delta.
I prefer cosine, but doesn't matter, same thing. Okay? If you add in, and this was the solution to our differential equation wherein the force MA was equal to negative KX, right? This is exactly the differential equation I expect you to be able to solve with C, this one actually, sorry, with C being equal to square root, or to K over M in this case. So what's omega here?
Root k over m.
Square root of K over M, yep. Where K is the Hooke's law constant on the spring. But if you're not using a spring, of course, we approximate everything as simple harmonic oscillators, so it doesn't have to be this. It doesn't have to be root K over M, that could be anything over there as it ends up. Okay, so for damping then, we assumed that there was another term that the acceleration was equal to, sure, negative kx, but minus beta times the velocity. Is that right? Was it beta squared?
Something damped oscillations mbx dot.
There's some 2 in there. Beta over
Where
2.
b over m is equal to 2 beta.
Yeah. Oh, I see.
So it would be 2 beta m x dot.
Yeah. And that just helps make the rest of the equation easier later, since we're defining a dimension, or you're defining a fudge factor, might as well define the fudge factor that's going to make your life easier down the road. So this is a minus.
It is minus.
And we then ultimately decided that this differential equation has a solution that looks like this, where x of t is equal to a e to the minus beta t cosine omega 1 t minus delta. Still have 2 unknowns, which are the amplitude, initial amplitude in this case, and
Phase offset.
phase offset. So those are the 2 I care about. And the way I look at this is, right, I group this together and this separately. So this is just the same solution you had before with a slightly modified frequency because of the damping. This is essentially the amplitude is exponentially decaying as you remain negative at. I lied though. This is the solution in what case?
In underdamped.
The underdamped case. Okay. And there are 2 other solutions. How about the critically damped case? Oh, that one's annoying, isn't it? There's that extra T term. Kind of here we go. C1T, C1 e to the negative beta t plus C2T e to the negative beta t. 2 unknowns now. Instead of amplitude and phase, it's the constant in front of each of these terms. What's the nature of each of these terms, you think? I think we decided that,
What's long term, what's short term?
yeah, this one is essentially responding to the initial velocity it might have, right? You have something moving very rapidly through the water that's going to really quickly slow down. And then this term that increases with t is the one that's actually being pulled on. And that's actually going to be, so this is obviously going to decay faster than this. So because this is increases proportional to t, but decreases according to e to the minus t, ultimately you're still going to 0 no matter what. But this is the fastest way to get to 0. Okay, case 3.
That's the overdamped case.
Is the overdamped case, in which case the solution is kind of a mess. C1 e to the minus beta minus square root of beta squared minus omega squared t plus t. So this is the slowest way to get there, because this term, beta minus square root of beta minus omega squared, it's always going to be lower than just e to the minus beta t by itself. So this is going to take longer to get back to the origin. But it's ultimately going to get you to the same place. And once again, somehow these conspire such that one of them is going to correspond to what's that initial response to the initial condition or initial velocity, and the other one is going to be the longer term solution. Which is going to be which? The one with the smaller coefficient before the t is going to be the one that's going to last the longest. Yeah. So I suspect it's probably going to be this one that's going to last longer, and this one's going to be more transient, but I'd have to think about that. Does that answer your question? Mm-hmm. Sort of a quick recap. Overdamped. Are there any problems? Yeah, Lagrangian problem from the back of the book that we haven't done yet that we should do. Oh, that one looks nasty. Did we do 729? Did I make you guys do that one on your homework?
No.
It's the one with this picture where you have a pendulum that's attached to a rotating disc. All right. Well, we're doing this on the fly, so we'll see how this goes, but let's try it. It's a two-star, well, I mean, it's a two-star problem, so already I'll tell you it's probably going to be more than I'm going to ask you to do on the exam, though. But like all the one-star problems I've already probably asked you to do, you know? All right, well.
There's like 2.
20.
We did the helix, maybe not.
We did the circular hoop.
All right, well, that was pretty boring, but. All right, who wants to do the boring one? Who wants to do the algebra-filled, exciting one?
Which one's on the test?
Looks like the vote's 1-0. Okay. 1 to 1.
Votes count.
And that's our government right there.
Yeah. 5% turnout. Yeah. Okay.
Oh, why are we doing this? Because nobody voted.
Alright, well, we'll do number 20 then. Alright, smooth wire is bent in the shape of helix with spherical polar coordinates rho equals r, and cylindrical polar coordinates rho equals r, and z equals lambda phi, where r and theta are constants and the z-axis is vertically up, with gravity vertically down. Okay, so here's z. It says there's a spiraling helix here with a given radius r, and parameterized z such that along this path z is equal to lambda times phi. So this is sort of like a slope, right? It's saying that the z-coordinate is changing regularly as you go around, and that's how it's parameterized the path, is by correlating. For each z, there's only one phi, so, okay, my drawing maybe looks a little funny in that sense. But for each z, there's one phi as you go down. And for each phi, of course, there's an infinite number of z's, each separated by times lambda. 2 pi times lambda. Okay? The question is, using z as your generalized coordinate, write down the Lagrangian, find Lagrange's equation, hence the beat's vertical acceleration, z double dot. And the limit that r approaches 0, what is z double dot, and does that make sense? Okay? What's step 1?
Right down to Lagrangian.
Okay? What are the kinetic energies in the problem?
1/2 mv squared.
What's the potential energy in the problem? Okay? Step 2, decide your Qn. Well, we already decided that. That's enforced in the problem to be z. So we're going to have to do this whole thing as a function of z. That part's easy. That part's going to be a little trickier. What are the components of the velocity? Z dot. So I think the velocity is going to be square root of z dot squared plus one other term.
R phi dot.
R phi dot squared. R squared phi dot squared.
R squared phi dot squared. Well, we need to get on in terms of z, so let's solve this here. Phi is equal to z over lambda.
So phi dot is equal to z dot over lambda.
Yes. R squared z dot squared over lambda squared. Okay. What is our Lagrange equation then?
Partial of L with respect to z is equal to time derivative partial of L with respect to z dot.
Okay, what's dl dz?
Minus mg.
Concur? dy dt of
1/2 times m times 1 quantity 1 plus r squared over lambda squared times 2 times c dot. So
the the 2's are gonna cancel, right? So it
that
should be
becomes
M
times quantity of 1.
Z dot, yeah, 1 plus
R squared.
R squared over lambda squared, yeah? And that's not changing with time. So this becomes minus mg equals d by dt m b double dot. Oh, I did that. Yeah? So the z acceleration depends essentially on this slope r over lambda, such that as r increases for a given lambda, essentially, right, the lambda corresponds to this distance, I think this is 2 pi lambda here, between successive peaks. So if the radius gets bigger, that distance stays the same, it's still lambda. As the radius grows, the effective slope that that particle has to go down is lower, and the z acceleration is proportionally lower. And that's the question in the problem. Make sure you guys get this.
If R goes to 0, it's just G.
Just G, just the, well, essentially if it's just, if R goes to 0, it's just a straight line, it just falls straight down. If it falls in G, that seems to make sense to me. Questions about that one? Too easy? Too hard?
Put a question like that on the test.
Yeah. This seemed pretty straightforward.
Yeah. That one's not too bad. Okay, questions about the Lagrangian then? About how it's going to be applied, about what I'm going to expect you to do? This is a good problem because you could solve it in 5 minutes. Or 15 minutes, which is what I'm going to give you, right? There's always pitfalls. If you make errors, I want you to have time to be able to go back and you know, reach it. If you realize you get to some result that doesn't make sense, like it doesn't have the right units or something, you know, you should go back and find your error. So I'm gonna give you more than 5 minutes to do this problem. But
Should we bring our own paper?
yeah. Well, I mean, I'm gonna have plenty of space on the page for you to, on the exam itself for you to work with. So, I mean, actually, you probably don't need to, unless you want to, you know, draw stuff on your own and sort of practice.
Okay.
I think you're all right. I will probably have the exam be just, you know, single-sided, such that if you really need space, you can always use the back side of one of the papers if you run into trouble. But yeah, I'd actually rather you do all your work on the page so that I can see all your work and figure out what's going on. You know, because if you just pop up with an answer for me, I don't know. I mean, that's not going to help me. I need to know where you got it. That's what I care about. Okay. Other questions about the exam? Everybody ready to do Lagrangians? Make sure you get your velocity right. Get all the components. Make sure you get all of your kinetic energy. All the kinetic energy in the problem. Okay? Well, we'll call it good. I'll see you guys tomorrow morning. We'll talk more about orbits as a brief interlude before the exam on Friday. The orbit stuff is not going to be in the exam, right? So you're safe on that. We'll be on the final though.
The final cumulative?
Huh?
Is the final cumulative?
Yes.
Class is
I will put Lagrangians on the final.
We expect the rocket equation on the first.
Potentially, but I would say that the rocket equation wasn't something that was a primary focus of the course. So my interpretation is that that probably wouldn't be something that I would expect to to give you an exam on at the end. I really don't know. The stuff that's the most important. I only have 2 hours to quiz you, you know, at the end. It's probably going to be mostly about the routines and oscillators. Same as kind of focusing on. Yep. The goal in the course is to get to the Hamiltonian by the last week or two. Yep. Because I want you guys to have seen that before the end. But we're not going to be able to get into it in the level of detail that I'd like. But I really want you guys to eventually be able to know, but we'll get started.
When are you offering the
Or,
astrophysics course?
It should be off
Like I
this
was reading
spring,
it,
so
Biz asked if
if
I
you
remember
haven't
it.
seen enough,
2:30 to 3:30.
I think it's on the list. That sounds right.
It was
It
there
may,
today.
it may have just been added.
On the B scandal list?
Yeah, just gotta
Class schedule, like the,
Oh, I just
click on the date, the year you know.
Because for a long time, like until right before advising us, so they just used the schedule from last semester for this.
Which is useless because it was, last spring wasn't offered, it's only offered every other year. So it should be in there, from, I'm pretty sure it is. Yeah, I think it's 2:30 to 3:30, Monday, Wednesday, Friday, which means,
In one of these rooms.
it kind of crimps my travel style to have the middle of the day, but it means I can fly back from the East Coast and land at Lewiston at noon and make it, so, that's what I think about.
What about that one guy who's in ROTC, I think, who's in visiting him? Jeremiah. He's like, is the test is the final gonna be cumulative or math goes? And you Chang totally didn't answer the question.
Yeah, that question, he's like, whoosh. Yes, my grading scale is 30, 30, 10, or, no.
It's whatever he wrote on the board. Some needs
No,
to be 85.
no, like how much was like test 1, test 2,
Oh, yeah, yeah.
homework, and I'm like, no, that's not the question.
That is a definition of cumulative, but.
It does add up to 100%, I'm glad.
Like, is
Yeah,
the final gonna be cumulative? No. It's still
Yeah, in
cumulative.
fact-
Like, if the answer is no, it's still.
Astrophysics will be right in here in this room, 2:30 to 3:30 next semester, Monday, Wednesday, Friday. So you guys, if you guys haven't had enough of me and orbits by then, you'll get it by the end. Yeah.
I'm never gonna go to class.
Here,
No
it
problem.
gives-
Yeah, it gives us
I'm done.
kinetic energy of the spring itself, assuming it has mass.
Yeah.
It says we have to find it, and it's 1/6 mx dot squared. And we have no idea what there.
Okay.
After that, it's just a Lagrangian.
Okay, well, I mean, I don't remember this, but let's look at it. I'm assuming you just have a spring here, right? And it's got some sort of total mass and some sort of total length. How fast is each part of it moving, right? So we've got this part at the end here is moving, where v is the total velocity, right? This is, must be moving at half v, this is moving at 0, right? So somehow you have to integrate, I would say, dm 1/2 dm v squared from 0 to L. And that's what I would do.
Okay.
To figure out what the total is. And then the answer is 1/6, so that's good to know where you're going with it. But I suspect it has to do with, right,
Has to do with the composition of the thing.
since the v squared here is gonna contribute 4 times more than the v squared here,
Yeah.
right, and that must be how it all comes out to 1/6. Well, in fact, you probably just integrate this, and this v, since we decided it's proportional to L,
I mean,
right, it's gonna be v naught times
Let's use that,
the position. Well, ultimately, we'll do this in x space.
as opposed to go straight.
dm will turn into somehow dx, and it's just become m out here.
There's nothing.
And then it's just be s cubed over 3, and then 1/6. So it's probably something like that,
Yeah,
just thinking about it.
that makes sense.
So give that a shot.
I can explain that.
Thank you.
Come on. Look at all this, and do that. So frustrated.
Did you guys not eat all the pizza this time? Man.
It's that pepperoni bell pepper one.
Someone finish that off so I don't have to take home. Can someone grab that for me? I mean, I could probably do it,
Yes.
but I don't wanna.
I'll make you a deal, you
Not
just
a-
find
not a
something.
fan of
online.
Okay, sure.
I don't understand how V turned into that.
So I was thinking about it in terms of.
You got it.
Desk.
I can
Looking
push
at,
it a little bit if that helps, but well,
So if you zoom in on right as the spiral is crossing the axis here. Thanks. Appreciate it.